So even if we're doing our sampling without replacement, we can still trust that our independence condition is met as long as this 10% condition holds, which says as long as our sample size is less than or equal to 1/10 the population size. We call p hat our point estimate because, as you probably already know, we're going to take p hat plus minus some margin of error to get an interval of values that hopefully captures this p. So let's start with the first part here. It says, what are the 3 conditions for constructing a confidence interval for a proportion? And then what happens if one of the conditions is violated? And we'll actually see that in one of the examples here in the notes. So there's 3 conditions. Let's start with 3 stars. I'm actually going to start on the bottom one here, and this is one that we know. There's a condition for independent sampling. So even if we're doing our sampling without replacement, we can still trust that our independence condition is met as long as this 10% condition holds, which says as long as our sample size is less than or equal to 1/10 the population size. Okay, and then what aspect of p hat does that actually prove? Well, this actually validates, if you remember from chapter 7, this is for the standard deviation. So the standard deviation of the sampling distribution for p hat. So once we have the independence condition good, 10%, if that works, we are free to use this formula for standard deviation. Okay, then I'm going to work my way up here. Normality is another condition we have to meet. And for proportions, that's actually the large counts condition, or the LCC for short. And all that says is NP greater than equal to 10 and N1 minus P greater than equal to 10. And actually, this is what we used last chapter when we assumed we knew what the true population proportion was. So in this chapter, we actually don't know what P is. So we're going to use the next best thing, and that's what we do as statisticians. We take sample data and we make inferences about the population. So all we have is P hat, therefore, that's what we're going to use. So we're going to add hats to these. So in this chapter, we better make sure N P hat and N1 minus P hat are both greater than or equal to 10. And there's one more condition we have to meet, and usually this is stated somewhere in the problem. We just have to make sure that things were done randomly, right? So a random sample was taken, or if it was an experiment, it was a randomized design. So that's the third and final condition we'd have to meet, is randomness. And there's nothing special we have to do for this one. We can usually just put a check mark and say the problem stated that the sampling was done randomly. So off to the side here, we know normality refers to the shape of the distribution we care about, right? So if we check normality, that talks about the shape of the distribution. You see my little normal curve there. And then apparently independence proves standard deviation, which is a measure of spread. So hopefully you see where I'm going with this by now. Normality, shape. Independence proves something about spread. Randomness then must prove something about our center being valid. So shape, center, and spread. That's really what these 3 conditions come down to as far as why we have to show them or prove them. And then the next part here, it says, what is the difference between the standard deviation of a statistic and the standard error of a statistic? So let me just scroll down here. Let's start with this. So in chapter 7, we got the standard deviation of p hat. That's the standard deviation of the sampling distribution, right? That was p times 1 minus p over n and then square root. Well, the only issue with that is we don't know what p is in this chapter, right? That's the thing we're trying to estimate. So instead of the standard deviation of p hat, we're going to run the standard error, which we're going to write the same thing except with p hats. And then the notation you'll notice is SE, capital SE, just stands for standard error of p hat. So in this chapter, this is the one we'll be using. Right? We don't know what p is, so we got to use the next best thing. We're going to use p hat for our standard error. And error is not a bad word here, right? Error just means how far we expect to be off. So the top one here, that was great for chapter 7 when we assumed we knew what P was, right? So for when the true P is actually known, we use this one. But more realistically, we're not going to know what the true P is. We're trying to get an interval of values for it, so we're going to use this one, the standard error of P hat. So that's used for when we estimate the true P using our sample proportion P hat. So a little bit more about the standard error. What's the formula? Actually, I gave it to you right here. How do you interpret it? And is it on the formula sheet? So for starters, no, the standard error one is not there. But you can kind of get it from this guy, right? We don't have the P's in this case, so we use the next best thing. We use P hats. Right? So I've already given you the formula for standard error of P hat. And it's a very similar definition to what we've seen before. So we can just say it describes how close the sample proportion, P hat, will typically be to the population proportion, which is P. And we're going to take that simulation approach. We're going to say in repeated SRSs of size n. So if we did this many, many, many times, this is about how far the P hat would be from the true P. So really similar to like a standard deviation definition that you've seen before, right? We don't say average for those definitions, right? We just say the typical distance. In this case, how far P hat will typically be from the true P. And then we have this simulation approach down here. If we did many, many samples of the same size, whatever size n is. Interpreting things like this, really common question on AP Stats tests, so keep that in mind. A lot of times they don't even ask you to calculate it. They'll give you the standard error. They'll just say, hey, why don't you interpret this in context? So you have to come up with something in regards to the definition of this thing. And again, no, it's not on the formula sheet, but you could pretty well come up with it. Just put hats on the P's. And then the next part here, it says, what is a critical value? We talked about that a little bit in the last notes. How is it calculated? And what's up with the star in the formula? So we know this so far. When we build our confidence intervals, we start with a point estimate, like an X bar or a P hat, whatever our sample data is. And then we do plus minus some margin of error. That's how we build our interval. So more specifically, the formula that's on the formula sheet for confidence intervals, it says this. Your point estimate is your sample statistic plus or minus some critical value times the standard deviation of that sample statistic. So I guess the margin of error piece comes down to this product, critical value times standard deviation of statistic. So this is what you'll actually get on the formula sheet as far as confidence intervals are concerned. So to get more specific, let's talk about a confidence interval for a proportion, right? The title of these notes. Our sample statistic will be P hat. That's our point estimate, our best guess. Plus or minus. So this critical value piece, that's our Z star. So that is our Z star. And I mentioned in the last notes, I think, that the critical value really comes from whatever Z score you want. And then the standard deviation of our statistic, look, see, right? Standard error of P hat, that's what we use in this case. We can't use the one with the P's in it from before because we don't know what P is, right? We're trying to build an interval that would capture that true P, and all we have is P hat. So this critical value really sets up your confidence level. So Z star itself measures how many standard errors we need to extend our interval above or below for our desired confidence level. So a rough estimate, right, a 95% confidence level would be plus or minus 2 standard deviations. So Z star would be 2. Actually, I think it's 1.96 if you calculate it, but roughly 2. And I'm using that 68, 95, 99.7 rule. If you wanted to go 3 standard deviations above and below, right, if Z star was 3 about, you would be almost 99.7% confident in your interval. So what's up with the star? Well, the star just means it's not from the sample data. All the other stuff in this interval, like the P hat and the square root of all the P hat stuff, I'm actually missing a parentheses there. Why didn't somebody say something about that? There we go. Got it. The Z star itself isn't from sample data, right? It's actually coming right off the chart, or use the inverse norm command in your calculator. It has really nothing to do with these. It just tells you how wide you want to go on a normal distribution. So the star is really nothing special. It just says it's not related to the sample data itself. So there you have it. This is the formula we're going to use to build confidence intervals for our proportions. We have p hat, our sample data, our sample statistic, plus or minus our z star, our critical value. That's just going to tell us how many standard deviations above or below we want to go on each side. And then our standard error of p hat right here. Is this in itself on the formula sheet? Great question. No, sorry. The general form is, though, right? The blue one, that's as good as we've got on the formula sheet. But this one actually is not on the formula sheet. So let's look at the first example here. It says find the critical value for a 96% confidence interval for a proportion. Okay, well, it would have been kind of nice if they said 95, because then we just estimate and be like, oh, that's 2 standard deviations above or below the mean. But we're going to have to get a little bit more specific, and we've got those skills from Chapter 2. So let's find that critical value, which is just our z star. So I'm going to draw the standard normal distribution. And then we can either use the z-score chart, although I prefer technology. I like the inverse norm command. And then we can find this z-score, or this critical value, if you want to call it that. So the standard normal curve, all the z-scores, let's see what I've got here. There we go, pretty symmetric. The mean is 0, the standard deviation is 1. This is the standard normal distribution. This is where all those z-scores come from. And if I want a 96% confidence interval, notice that this curve is perfectly symmetric the way I drew it. Not really, but you could imagine. So a 96% confidence interval, let's use that symmetric idea. Let's make 2 bounds here and try to roughly estimate if I shade the middle 96%. The question is, where are these 2 bounds at? If that's the middle 96%, where are those 2 bounds at? Because that will tell me what my critical value is. And as far as the proportions are concerned, if there's 96% in here, well, that means that this bound would have, well, it would be at 0.02, right? The second percentile. And this bound would be at 0.98. How the heck am I getting that? Well, if there's 96% in here, that means I have 4% left over out of the 100% to split up between these 2 tails. And since it's perfectly symmetric, you know you have 2% to go here and 2% to go there. So the percentile for this would be 0.02, percentile for that would be 0.98. So you can look up either one of those percentiles on the z-score chart, and it'll give you our critical value. Now one will be positive, one will be negative, but otherwise same value. I like to use inverse norm. So if I use inverse norm, and then for my area, I'll use the 0.98 marker. You could just as easily use 0.02 if you want. Mean 0, standard deviation 1, because that's the z-score distribution. Right? Nothing special for mean and standard deviation. That's our default z-scores. That should give you 2.05 for the z-star, meaning this boundary would be 2.05 standard deviations above, and this one would be 2.05 standard deviations below. Cool. So all that fun drawing and theory just to tell you, if you want 96%, well, it's 96% in the middle, so that bound would be at either 0.98 or 0.02. Just do inverse norm, or look it up on your z-chart for 0.98 or 0.02. And what do you know? 96% is a little bit bigger than 95%. The z-score is a little bit bigger than 2 standard deviations above or below. The next part here says, what is the formula for a 1-sample z-interval for a proportion? And I don't want to get too in-depth with the 1-sample, 2-sample stuff right now. Just for now, I just want you to know that that's like calculator speak. So there is some stuff within your calculator that you can come up with these intervals with. It's called a 1-sample z-interval for a proportion. We'll also do stuff with 2 samples, and we'll do some means and some other stuff too. So for now, 1-sample z-interval, that's what we're doing. That's the name of it, and we'll refer to that when we get to the calculator commands also. Is it on the formula sheet? Yeah, we wish. We wish. It's actually not there, right? I talked about that before. They just have that really general one. This is the one that we have. P hat plus minus that critical value z star times the standard error of p hat. And I just want to color code each one of these pieces. In purple, the condition that goes with the standard error thing, that was the independence condition, right? The 10% condition. So if that works, this part for the standard error, which covers our spread, is valid. So if the standard error, that's a measure of spread, that goes with the 10% condition, you could probably guess what goes with z star. So if that comes from the standard normal curve, that would be the large counts condition. So if that's checked, that means our shape is confirmed. And then we only have one more condition left, if you'll remember. It's the one about randomness. So if the data was obtained randomly, that means we can trust that our p-hat's good, and that's going to be our measure of center. And it's definitely our point estimate, therefore it's the center of our confidence interval. So I'm not going to ask you to express it like this. I just want to give you an idea of which condition goes with which piece, and then whether it's shape, center, spread, which one goes with which component as well. So that's it. That's our formula. Unfortunately not on the formula sheet, but we should be okay to come up with it. The general formula, this guy, is the one that's actually on the formula sheet. All right, then let's look at the last example for these notes. It says students in an AP Stats class want to estimate the proportion of pennies in circulation that are more than 10 years old. To do this, they gathered all the pennies they had in their pockets and purses. Overall, 57 out of the 102 pennies they have are more than 10 years old. Part A says identify the population and the parameter of interest. So remember, parameters are things that describe the population. That's something that we're trying to estimate. So part A, the population, I guess, would be all the pennies in circulation, like everywhere. And then the parameter is this characteristic about the population that we want to know. And that would be the proportion of pennies that are actually more than 10 years old. So of the population, what's the true proportion of pennies that are more than 10 years old? Okay, interesting enough. Part B says check the conditions for calculating a confidence interval for the parameter, which in this case would be the true P. So let's start with randomness. Let's see if we meet that condition. Well, it's not like they did an SRS or randomly sampled pennies. So there's kind of an issue with that. The data are not obtained randomly here. They're not from an SRS. So I want to hold on to that for a second. Like, wait, so they're not no. I mean, they just dumped out all the pennies that they had and they looked at those. So that's not a random selection from the population. So this condition's actually no good. I want to come back to that in a second. The other conditions, let's start with normality. N times p hat in this case, so our sample size is 102. P hat was our sample proportion of pennies that were actually more than 10 years old, so that was 57 out of 102. That simplifies really nicely, that's just 57. And N times 1 minus p hat is equal to 102 times, well, the leftover. Right? If there's 57 successes, there must have been 45 out of the 102 that were failures, so that's 45. So N p hat and N1 minus p hat are both greater than or equal to 10, so we can assume normality is good. In other words, the large counts condition is met. And it was in fact easily met here, right? P hat 57 out of 102, so 57 successes we'll say, and N1 minus P hat 45 successes. We're way over 10 in both cases, so no problems with the normality. Okay, and then lastly for the conditions, as far as the independence condition is concerned, I think we're good, right? They sampled 102 pennies. And if we do 10 times 102, That's 1,020 pennies, right? Just add a 0 to it, which is definitely less than the population size of all pennies in circulation. So we are clear. We are good to go on the 10% condition. We're way under 10% of all the pennies in circulation. So this one's good, independence. Normality's good. The randomness, though, we got an issue. Like, it definitely wasn't random. So if you look back at the beginning of the notes, there was this piece that said, what happens if one of these conditions is actually violated? Well, we can still run the numbers, right? We can still build the confidence interval and do all the stats. We just need to make that, point clear, right? So we're not trying to hide it from anyone. When one of these conditions is violated, let's just say, hey, by the way, this is violated, proceed with caution. Right? That's an important piece. So we're not trying to be sketchy statisticians or anything. We're just going to say, hey, by the way, this one wasn't met. Just so you know, we're going to proceed with caution. So that's what we should have stated here. The randomness condition was not met. Therefore, proceed with caution. So that's an important piece there. What do we do if a condition isn't met? Okay, well, we'll just note it in the plan step. All right, and then part C says construct a 99% confidence interval for the parameter. So we have our p-hat, that's 57 out of 102 for our sample data, which is 0.559. So we take our p-hat plus or minus our z-star times the standard error, which 0.559 times 1 minus that would be 0.411 over our sample size of 102. So no big deal to come up with p-hat and the standard error of p-hat, right? You just do p-hat, 1 minus p-hat over n, and then square root it. We still need this z-star, though, this critical value. So if we want a 99% confidence interval, well, just think about if the inside 99% is covered, that leaves us with 0.5% on each side, right? So the area we should tell our calculator, or the area that we should look up on the z-score chart, would be 0.995. And that gives us our z-score of 2.56. And if you have a hard time following, like where the heck is he getting 0.995, let's just draw it. All right, let's draw the standard normal curve. And I'm going to mark off two boundaries. I'm going to try to shade 99% of this thing. So if I can shade 99% of it, right, so the area inside there is 99%. Well, how much area is left in these little tails? All I've got is 1% left, and I've got to split it up. So that means I have 0.005 in this tail and 0.995 underneath this tail, right? Because there's 0.5% for each one. So whether you want to use 0.995 or 0.005, one of them would give you a z-score of 2.56. That'd be the positive one right here. That'd be 2.56 for this z-score, and this z-score at this boundary would be negative 2.56. So if you're wondering where I'm coming up with these z values, I'm using the fact that the curve is symmetric, and I shade the inner whatever percentage it is. In this case, it was 99%, and I look to see what percentages would be at these boundaries. And then once I know that, I use inverse norm, or if you want to look it up on the z-score chart, that's great also. And I get a z-score of 2.56, so that's going to go in here for my critical value. Okay, and if we calculate the margin of error here, multiply 2.56 times the square root thing, we've got 0.559 plus minus 0.12585, so that's our margin of error. So now let's go ahead and add it for our upper bound and subtract it for our lower bound, which gives us our interval of 0.433 to 0.685. So part C is good. P-hat, critical value, standard error of p-hat. There's our interval. Part D, of course, we can't get through this without having to interpret this thing in context. So part D, we are 99% confident that our interval from blank to blank, whatever the lower bound and upper bound is, our interval from 0.433 to 0.685, captures the true, whatever we were looking for again, right? The true proportion of pennies in circulation that are more than 10 years old. Remember, I gave you that structured cookie-cutter approach for these problems because it's such a common problem for this chapter. Interpret this interval in context. We are blank % confident that the interval from blank to blank captures the true blank, whatever that is. Use context words from the problem. All right, and the last bit here, and probably the most important piece for a statistician. Is it plausible that more than 60% of all pennies in circulation are actually more than 10 years old? And you need to use the interval to answer that question. So is it plausible that actually more than 60% of all pennies in circulation could be more than 10 years old? And I think our answer should definitely be yes, right? Our interval goes up to 0.685, so the fact that our interval includes 0.6 and goes above it even, that suggests that it's definitely plausible, right? Our interval is a bunch of plausible values for P. So for part E, yeah, it's definitely plausible. Why? Because our interval contains values of 0.6 and above. So we would say it's certainly plausible that P could be greater than 0.6. And remember, P is the true population proportion of pennies in circulation that are more than 10 years old. So part E, probably the most important question of all these questions. You're a professional statistician. What do you think? Is it plausible that more than 60% of all pennies could actually be more than 10 years old? Well, based on this confidence interval we found, it looks like it's definitely plausible, right? Heck, it could be even 68% are more than 10 years old based on our interval, right? All right, so we talked about the conditions for these confidence intervals. We talked about the formula for standard error of p hat. We talked about the actual formula for calculating a confidence interval for a proportion. And we went into detail about critical values, and we'll need those for the next section too on means as well, the z-score stuff. So that is all for these notes. I'll see you in class.